All right, so this is where we left off. So we were looking at this word problem, and I know what you probably think. Oh my God, a word problem takes up an entire page. What am I going to do? Actually, this is one of the simplest word problems that you can solve. You just have to be careful and not get all, bent out of shape by the fact that it's a really long word problem. All right, so we're going to look at the word problem and try to figure out what you've got. All right, so we've got 1.5 liters. Now, what are liters the units of? Volume, right? So we're going to say volume. I have 1.0 atmospheres. What's the atmosphere units for? Atmosphere is the unit of pressure. We have 298.14 Kelvin. Kelvin is something that deals with temperature. All right, then we've got 0.53 liters, volume again, 1.2 atmospheres, pressure again, and then we're asked for the new temperature. So this is temperature. Now, you notice that you actually have 2 volumes, 2 pressures, and 2 temperatures. So we know that this can't possibly be the ideal gas law problem because it has 2 of everything. And the only equation that we know where you have 2 of everything is that combined gas law equation. So we know we're going to have to use the combined gas law. Just to not get ourselves confused by the fact that there are 2 volumes, so we don't mess up the volumes and say volume 1 is volume 2, let's go ahead and number which one is which. So we're going to go ahead and say that this is volume 1. Now read the question carefully, because if you're not, you'll get confused and you'll give the wrong pressure, because when you give a word problem, you don't always have to have volume 1 followed by pressure 1 in the word problem itself. You have to read the question. So it says you take a sample of gas that occupies 1.5 liter volume at 1.0 pressure. So this goes with that volume. So we're going to go ahead and say that that is pressure 1. And it is at this temperature. So that's all the same gas that we're talking about. Pressure 1, volume 1, pressure 1, temperature 1. And then you transfer the gas to a new volume. So this is going to be our volume 2. And volume 2 is at this pressure 2. And we're looking for the temperature at this new, in this new container. Okay, so we've got all of our things labeled. We're going to go ahead and write out our equation. And then we're going to put all the units with all the numbers that go with the appropriate symbol. So the equation that we're going to use is our combined gas law equation. Which, if you remember, is basically the PV is equal to nRT divided by PV is equal to nRT without the nR being there. So this is, we can just go ahead and write P2 times V2 divided by P1 divided by P1 is equal to T2 divided by T1. So there's my combined gas law equation. And why did I not write 1 on top and 2 on the bottom? Well, because the equation solves for T2. If I have T2 up here, it makes the algebra a little bit easier than if I have the T2 down here, because then you'd have to flip the equation. So if you sort of look at the equation and do it that way, you save yourself a little bit of algebra time. But it would not have been incorrect to have used the other equation, to have had the equation P1 times V1 is equal to T1, and then 2 on the bottom. That would have been perfectly fine. But we can use, if you do this, you'll save yourself a little bit of time. Or you could have numbered these 1, 1, 1 instead of, and number these 2, 2, 2, and it would have ended up with the same thing. Okay, but let's go ahead and label what each of the numbers are in my word problem. Okay, so I'm going to go ahead and write down V1, P1, T1 is equal to, and then I'm going to write out V2, P2, T2 is equal to. All right, so we look at V1, I see 1.5 liters. Don't forget to write out the units. pressure 1 is equal to 1.0 atmospheres. And then my temperature is 298.14 Kelvin. All right? And then we can look at the other part of that problem. So we've got volume 2 is 0.53 liters. Our pressure 2 is 1.2 atmospheres, and temperature 2 is unknown. So we don't know what that is. All right, so there we are. We've got our equation. We've got all our variables that we're going to plug into our equation, and we can plug it in and come up with the correct answer. Now, granted, when you have pressure in, let's say, torr, and you got another pressure in torr, it deceptively looks as if you can go ahead and use the same units as long as they're the same units. But it sometimes appears as if it will work, but it often does not. So if you use, for instance, volume of cups or something like that here, it doesn't really work. So even though we don't actually have explicitly an R value where everything will cancel out, my suggestion is go ahead and use the units that are provided. Although sometimes you can get away with using whatever unit you have without making a conversion. But in this particular case, all the units are exactly what you would expect, so this is going to be a sense, and all we have to do is plug in the numbers as given. So let's go ahead and plug in the numbers into my equation. And my suggestion is, if you're going to get partial credit for setting up the word problem, my suggestion is go ahead and plug it in. Probably if you're good with algebra and you're sure you're not going to make an algebra mistake, it's probably easier to work with the formula symbols instead of working with the actual numbers. But it doesn't make any difference really one way or the other because you're going to come up with the same answer anyway. All right, so but my suggestion is, for the purposes of getting partial credit, go ahead and plug in. Because as long as you've plugged things in, you've essentially done all of the chemistry part of the problem, and then the rest of it is just algebra. Okay, so you get partial credit differently for doing the chemistry part as opposed to having the algebra done incorrectly. All right, so let's go ahead and plug in. So we're going to say T2 is 1.2 atmospheres. Keep all the units there, because if you forget the units, you will confuse yourself and come up with the wrong answer. My volume 2 is liters, 0.53 liters. And then I've got pressure 1 is 1.0 atmospheres. My volume 1 is 1.5 liters. And then my T2 I don't know, so I'm just going to leave it T2. And then my T1 is 298.14 Kelvin. Let's take a look at the units and make sure that they all cancel out. Atmospheres cancels atmospheres, liters cancels liters, and this temperature that I get is going to be in Kelvin. So let's go ahead and plug in all the we'll do a little bit of algebra, do a little bit of rearranging. And all we're going to have to do, because we actually put the T2 on top, is I'm just going to have to multiply both sides of the equation by 298.14. So here we go. So we're going to say 1.2 atmospheres times 0.53 liters divided by 1.0 atmospheres times 1.5 liters. And then we're going to say times 298.14 Kelvin is equal to T2 divided by 298.14 Kelvin, and then we're going to multiply 298.14 Kelvin over here too. And of course you realize that my 298 Kelvin will cancel my 298 Kelvin. So then I end up with T2 by itself on this side of the equation. And then all I have to do is plug in those numbers, crunch the numbers through, and I get 126.4 Kelvin is equal to T2. People usually write the variable on the left side and the actual number on the right side as a general rule. So we're going to go ahead and do that. The other thing I noticed is that I only have two significant figures in my pressure and in my volumes. So I can only have 2 significant figures in my final answer. I don't usually count off much or at all for incorrect significant figures, but to actually get the correct number of significant figures, I'm going to say that this is going to be 1.3, because we're going to round up, times 10 to the, and we can move that decimal point over, so 1, 2, so 10 to the second Kelvin is equal to T2. So there we are, end of that word problem. Okay, so now we're going to do another word problem in which we're going to, well, let's look at the word problem. And what you will find is that this is actually one of the little simple gas laws that I can go ahead and solve it using the combined gas law. Go ahead, let's go ahead and put the word problem here. So here's my third example. All right. So in this word problem, we're going to say if at 35 degrees Celsius, the volume is 3.50 liters, after heating the sample, if the volume becomes 7.00 liters, what is the new temperature? And you are to assume constant pressure. Okay, so there we are. There's our word problem. All right, so now you notice that this is actually at constant pressure. So we want to analyze the question. So you got, this is temperature, this is volume, and then here's volume again, and here's the new temperature. So let's go ahead and label these. So let's say this is T2, and this is V2, and then this becomes V1, and this becomes T1. We've got constant pressure, so we can actually leave that pressure equation, pressure out of that equation. But what we're going to do is we're going to actually use the combined gas law equation, because on the exam I will only give you the combined gas law equation. Now you could have memorized the Boyle's law equation or the Charles law equation and look at it separately, but I'm only going to give you the combined gas law equation. So we're going to go ahead and use the equation that I will provide for you. All right, so here we go. We're going to put down all the variables, and then we're going to label, we're going to come up with the numbers for what all of these things are. So you got okay, so temperature 2 is 35 degrees Celsius. Volume 2 is 3.50 liters. Okay, so you got temperature 1, volume 1, and pressure 1. Temperature 1 is question mark, we don't know what that is. Volume 1 is 7.00 liter. And pressure 1, it says at constant pressure, so that means that I can either set P2 is equal to P1, or I can say P1 is equal to P2. But I'm going to say that they are equal because it says at constant pressure. Now, the other thing we have to watch out for is this is in liters, so that's fine. We can use that unit. But this is in degrees Celsius, and we know that when we do our temperatures, we really need to have temperatures in Kelvin. So to convert from degrees Celsius to Kelvin, all I really have to do is add 273.15, oops. And that's going to give us our temperature 2 in Kelvin, and that is going to be 308.15 Kelvin. So there's my temperature in Kelvin. Right, so now we're going to plug it into our combined gas law equation, the variables that we have found. And here we write out our combined gas law equation. So we're going to say, now we're solving for T1, so we'll just keep the 1 values on top, just to make it easier. So we're going to say pressure 1 times volume 1 divided by pressure 2 times volume 2 is equal to T1 over T2. So there's our equation. And before we start, we're going to go ahead and plug in, and we're going to say, in place of P2, I'm going to go ahead and put in P1. So my equation then becomes, after I plug in, I'm going to say P1 times V1 is equal to P1 times V2 is equal to T1 over T2. So now you realize that my P1 will cancel my P1, so that really goes away. And this now becomes one of the simple gas law equations. So if you remember the simple gas law equation where you had just pressure and temperature, which is Charles's law, there we are. But we don't have to memorize Charles's law separately. I might, on the next exam, I might ask you something about the multiple choice, and perhaps in the multiple choice question, something about the difference between Boyle's law. But for the purposes of our equation, I will give you the combined gas law equation, and you can always derive Charles's law or Boyle's law from the equation given. Because if the pressures are constant, they cancel out. All right, so let's go ahead and plug in all the values that we have. I'm going to stop for a minute here and, well, okay, let me go ahead and finish this up. So I'm just going to go ahead and plug in all the values that I have. So I've got volume 1 is equal to 7. Volume 2 is equal to 3.5 liters. My temperature 1 is unknown. And my temperature 2 is 308.15 Kelvin. Do a little bit of algebra. I get T1 is equal to 616 Kelvin. And if I want the new temperature in degrees Celsius, I can just simply subtract off 273.15, and then I will get 343 degrees Celsius. Once again, I had 2 significant figures in my original temperature, so I should really only have 2 significant figures in my final answer. So I should really report this as 3.4 times 10 to the second. So 2 significant figures. And there we are.